had your hands on the instructions for the lab this afternoon. So what I'll do is I'll circulate these among the audience, and then we'll have the leftovers for the labs this afternoon. So this is a handout. So this talk and the notes that accompany this talk are also available on the summer school website in the program. You can click on that. And this is a fairly comprehensive talk, slanted to things that I'm more familiar with. Because of that, I won't have time to make mathematical arguments, so I will avoid doing that. Also, we'll look at a number of equations. I won't discuss them in detail, but rather I'll discuss them in the same way that my colleagues talk about molecules. They don't talk about every atom. I won't talk about every symbol in these equations. And at the very end, I'll give you a brief demonstration of how to use a Mathematica notebook. You don't need to know Mathematica, but I find Mathematica to be the most convenient way in order to do a set of calculations and to repeat them and to change things. And so that's what we'll be using. So when we look at a simulation of the results of a simulation, what we see is some semblance of reality distorted by modeling errors, slightly obscured by numerical artifacts, and possibly compromised by programming bugs. And for this reason, it's useful to know about numerical artifacts. First of all, we can discount them when we look at the results. And secondly, if we know what to expect and we don't see what we expect, then that's a good sign that there are bugs. So I'll be talking about just a subset of these topics here. Here it indicates there's two kinds of approximations. Clearly, the better kind of approximations are controlled approximations. Let me mention some useful references. At the top in red are the two that I refer to most often. This is a fairly recently published book by Professor Schlick. It's a rather remarkable book because it's printed in a number of colors. It's just a beautiful thing to behold, and the price is not that high for a book printed in colors and having so many pages. I spoke to the publisher of that book, and he said that if the book goes out of print, they might be reluctant to reprint because it's in color. So my advice is if you wish to own the book, not to wait too long. Another reference, because it's fairly old, that I find good is this book by Ellen and Tilsley. It's a well thought out book. And this reference here I list because this is slanted towards biomolecules. This reference here is slanted towards material science, but I often see it cited, so I've got to include it here as well. This is an outline of the talk. First, in order to talk about algorithms, we need to know what the target is, what it is we're trying to compute. And so I will begin by discussing what it is that we're trying to compute. And actually, it's not that obvious, especially people not familiar with the subject of what we're trying to compute. So these are equations that you are quite familiar with. The main reason for putting them up here is to show you what notation I'm going to use. And most of these symbols are fairly familiar, except possibly not everyone uses U to denote the potential energy. So these are the equations of motion, but I prefer to write them in a more concise form. I prefer to because it makes getting rid of the clutter makes it much easier to see what's going on. So I'll let X denote the collection of all positions. So this is a vector of length 3n. This is a matrix 3n by 3n. This is the collection of vectors. This is the collection of momenta. This is the collection of all 3n force values. Such notation is widely accepted as evidenced by the popularity of the language MATLAB, which forces you to use vectors to represent everything. Another way of writing the equations of motion are, instead of writing them as a second-order system of ordinary differential equations to write them as two first-order systems. One equation for the positions and another equation for the momenta. And associated with this is a Hamiltonian. The Hamiltonian generates the system of differential equations. The Hamiltonian expresses the energy as a function of positions and properly defined momenta. In the potential energy function, the most problematic terms are those having to do with electrostatics, because electrostatics is a very long-range force. And this is particularly problematic in the case of periodic boundary conditions, because what we would like to do is to simulate a given box replicated infinitely often in all three directions. And so the natural thing to write down for the potential energy is a term like this, where we sum not over all I particles within the box, I and j, but we sum over all images of the initial periodic box. Unfortunately, because of the nature of the slow decay of the electrostatic force, this sum is not well defined. The result of computing this sum depends upon the order in which you sum the terms. And so more has to be said about what we mean when we say we want periodic boundary conditions for electrostatics. And so one way of expressing what we want is to, instead of imagining we have an infinite number of periodic boxes, imagine that there's this huge, huge sphere filled with periodic boxes. And outside the sphere is some medium with dielectric constant epsilon sub s. S stands for surroundings. And if we do that and then take the limit as the infinite, as the radius of the sphere goes to infinity, then we get the following formula for the electrostatic force. How visible is the green? Well, it's not too important because the green was chosen because it was to be less visible. And we get a sum involving terms like this. This is fairly complicated looking, and I won't discuss the individual terms. Let me say, though, that the famous Ewald sum consists of the first three of these terms. And this fourth term is a consequence of the dielectric medium outside this very large sphere that we imagine that we're doing the simulation inside. This fourth term is probably best neglected. It usually is neglected. First of all, one can argue that it's quite small because the dielectric coefficient of water is large, because large is usually the surrounding medium. And secondly, this has the unpleasant property of not being continuous as a function of particle position. If a particle leaves the periodic box and comes in through the other end, there will be a jump in this term. That will cause problems if you do dynamics. That hurts you if you're trying to do minimization. Okay, now I'll discuss in the next two slides what it is we're trying to compute using the model that I just discussed. And I like to divide the aims into two different kinds, kinetics and thermodynamics. In kinetics, we're interested in time-varying quantities. However, there's a big problem. Namely, the equations of motion are chaotic, very chaotic. After 10 or 20 picoseconds, all we see in our simulation are the effects of round-off error, even if we're using double precision. And so we cannot attach any accuracy in the traditional sense to a single trajectory after not so long time. So how do we make sense then of solving ordinary differential equations that are chaotic? Well, first of all, we have to acknowledge that we don't have perfect information about the simulation. And so we should put our uncertainty into the model. And this is usually done by choosing the initial velocities at random. So we incorporate uncertainty stochastically. So in some sense, we have a stochastic problem to solve. And secondly, since we have a stochastic problem to solve, we should only ask for averages and not ask and not put too much weight on a specific trajectory. So therefore, as an example, suppose that we have an observable A, and A might be defined as follows. A might be defined to be 1. Well, suppose that we divide configuration space into a finite set of conformations, and A has the value 1 if we are in conformation X and is 0 otherwise. And therefore, the expectation of A represents the probability of being in this conformation. And I'm using gamma here to denote a point in phase space, which consists of a point in configuration space plus the collective momenta. And so the way that we might compute this probability, the probability of being in a given conformation X, is that we might run a number of trajectories, which are initially, say, in some other conformation Y, randomly chosen in conformational Y with a probability density function given this way. And after running this ensemble of trajectories, then we might take the average value of A, and that gives us the probability of being in the given conformation X. So this is a kinetics type of calculation, a long-time kinetics type of calculation. People also do short-time calculations involving time correlation functions. However, most simulations, in fact, ask different types of questions. They ask thermodynamic questions. They ask, what is the average quantity of some observable over phase space given some probability distribution defined on phase space? And there are standard probability distributions corresponding to NVT and NPT. And the way in which we usually do this calculation is we generate these state vectors at random, usually in a sequential manner using some propagator, which might be a Monte Carlo method or it might be molecular dynamics simulation. And then we take an average. Let me mention something stated much earlier in the summer school, and that is that there are some calculations which are not practical today for biological molecules of reasonable size. That is, in practice, for biomolecules, we can't actually compute a reliable value for quantities like that. And so we have to state exactly how much simulation we did in order to get some estimate of it. And so this is the more common type of calculation. And the important point I want to mention is that the propagator that takes us from one state vector to the other state vector does not have to do correct physics. It just has to sample from the correct ensemble. So those are the two aims that should guide the development of algorithms. And I want to make a few comments about reduced models, ways in which we simplify the standard atomistic model in order to reduce the amount of computation. One way is by imposing constraints on the lengths of bonds and angles. And this has the effect of removing the highest frequencies and enables integrators to use longer step sizes. The constraints are typically represented as a set of quadratic equations which are more concisely stated this way. So that means that our equations of motion here are augmented by these algebraic equations. So in order for the problem not to be overdetermined, we have to add an equal number of new variables, which are the Lagrange multipliers, which tell us what the magnitudes of the constraint forces should be. So this is something that we might add to our model. This is a decision that has to be made. But there are implications as far as implementation. It can be complicated to try to impose constraints if we're doing a parallel simulation. Okay, another compromise we might make in our model is not to explicitly represent the waters, which typically make up 90% of the simulation. But their effects have to be represented somehow. And this is done by augmenting the potential energy function with the solution of a Poisson-Boltzmann equation to account for the electrostatic effects of the implicit waters, by adding a friction and a noise term which takes into account the collisions with the water molecules. So first of all, let me say that there is a compromise in accuracy, and a recent study has shown that implicit solvent deviates from explicit solvents unless 4 layers of explicit water included. And then, let me also say that to implement something like this is quite complicated. Even though it can potentially save you a lot of CPU time, it is non-trivial to implement implicit solvents. And for this reason, even simpler models have been devised. Okay, so that's an overview of the equations that we might be interested in solving by means of algorithms. And now I'm going to discuss algorithms in 3 different categories: the evaluation of forces, integrators for doing long-time kinetics, and propagators for doing thermodynamics. Okay, first, the question of computing the forces more rapidly, because that's where all the CPU time is spent, particularly for the electrostatic forces. First, I'll discuss the case of non-periodic electrostatics and fast methods for doing this. And there's two categories of fast methods that have some things in common. One category I call cell methods. In fact, this word has been used by others. And the most famous of these is the fast multiple method. And these are based upon an octree decomposition of space. And there's another class of methods which are hardly known at all, which are called grid methods. And because I, in fact, prefer these methods, I'll discuss them as well. And so both methods, these multi-value methods, both have the property of trying to do a separation of spatial scales, so that we separate short-range interactions, of which there are only order n, from slowly varying interactions, of which there are order n squared. And in order to economize on the computation, the slowly varying ones are approximated. So all fast methods depend upon approximation. The difference between these two types of methods is between the cell methods and the grid methods is based upon the way in which they separate length scales. So let me begin with cell methods, such as the fast multiple method. For every interaction, that is, for every pair of particles, the interaction is represented either directly or at the finest level, or at the bottom of the octree, or at the next level up in the octree, or at the next level up in the octree. So every interaction is represented once at one of those levels. And economies are made because at the higher levels, what we do is we pool the effects of the particles, so that in the end, in computing this interaction with that interaction, we only compute one interaction. Well, this, as you know, probably know, is a fairly complicated algorithm, and I'm certainly not going to discuss many details. But let me say that, of course, an approximation is necessary, and this approximation is based upon a Taylor expansion of the potential. Now, because the potential is 1 over r, it is a harmonic function, and it turns out that the truncated Taylor expansions are harmonic functions, and so they can be economized, and hence we get fast multiples that way. The other class of methods are grid methods, and they do the separation of spatial scales in a different way. Instead of representing each interaction only once at one of the levels, each interaction may be represented once or twice or 3 times or as many times as is necessary. Because these grid methods, what they do is they take the potential and they split it into 2 potentials. Into one potential which is a softened version of the 1 over r potential, and the other potential which has a finite range. So this is the separation of scales, but approximation is needed for the slowly varying part, and this approximation is based upon an interpolation from a grid. And the advantage of grid methods over cell methods is that it's easier to implement forces which are continuous. That is, continuous as a function of particle positions. If the particles move, what happens to the energy? What happens to the force? Does it change continuously or does it jump? Well, for the fast multiple method, it jumps. And if these jumps are too large, the effects can be seen in the numerical simulation of the dynamics. So as it's stated here, the multiple method is not usable unless we use high accuracy. And here's an example. Here I'm showing you 3 different energy curves. This one here, in which the energy rises over a mere 1 picosecond, is one in which we used 8 terms in a fast multiple expansion. If we use 12 or 16 terms, then the energy, although it also fluctuates, does not drift. And so partly because of this, and partly because of the complexity of the fast multiple method, for molecular dynamics, in one test that we did, the multiple grid method was 4 times faster. This is not a statement in general about preferring multiple grid methods to fast multiple methods. This is in the particular context of molecular dynamics that this statement is made. Okay, so I mentioned the importance of having continuous forces, because empirically it's observed that if the forces are not continuous, then we have upward drift in the energy. And so just a note about the use of NAMD. In using NAMD, it's, for example, for the van der Waals forces, it's recommended that you turn switching on, and which means you have to choose a switching distance and a cutoff and another parameter. Okay, so that was a discussion of the non-periodic case. Now I'll briefly mention the case of periodic boundary conditions with long-range electrostatics. Assuming that we want to use an Ewald sum, there comes the question of how we implement it, which approximation, and we have to approximate it as we're going to use. Are we going to use a standard Ewald approximation, which is simply a question of taking those sums which I showed you earlier and cutting off the Fourier series, and as well as cutting off the potential for the short-range force? Or as an alternative, there's the particle mesh Ewald algorithm, which is closely related to particle-particle-particle mesh. And it does the approximation by interpolating the Fourier basis functions from a grid. And this has the effect of turning a Fourier series into a discrete Fourier series. A discrete Fourier series is a finite sum, and it can be rapidly computed using a fast Fourier transform. And so in choosing between the two, this one gives better performance with the same accuracy. But of course, there is the necessity of having an implementation of the fast Fourier transform, which is efficient on a parallel machine. So this is available in AMD, and you control the accuracy by setting the tolerance, and this has to do with the short-range part. It actually has to be cut off because it does have infinite, although negligible, infinite extent, but it's negligible at large values. Okay, so that was a discussion of the fast evaluation of forces. So for the remainder of the lecture, I'll talk about integrators and propagators. And mostly I'll talk about integrators for Newtonian dynamics, and then I'll briefly mention what we do for constrained dynamics and stochastic dynamics. Okay, so the well-known method for advancing the solution to the equations of motion for molecular dynamics is the method associated with the name of Verlet. It's a very simple-minded method in which we approximate the second derivative of the position by means of the centered difference. I've written it as a discrete analog of the differential equation. To actually implement this, of course, one has to rewrite this equation so that we've solved for the positions at the new time as a function of the old time and the time before. The question of the accuracy of this is an exercise 5 in the numerical lab this afternoon. We might be interested in calculating the energy, and for this purpose, we need a velocity definition. So the definition of velocity that usually goes along with Verlet's method is the centered difference here. An important point is that how we define the velocity does not affect the dynamics, as you can see. So it's a relatively minor question. Relatively. Now, for the purpose of implementation, it's probably better to use a different form of the Verlet method known as velocity Verlet. By means of some not quite so trivial algebra, one can rewrite the Verlet method so that it looks like this. And this is intuitively more appealing because what we see here is a mapping from a set of positions and a set of velocities at time n to positions and velocities at time n plus 1. Although I've written these equations in the form where we're actually solving for the new momentum in terms of the old momentum. So typical integrators for doing molecular dynamics can be written more concisely in this form here as a mapping from one point in phase space to another point in phase space. This implementation is better because it is less affected by round-off error, for example. Also, it's easier to see how to get started. How do we start? Well, we start by choosing the velocities at random. Now, I stated earlier that we have this big problem in that the equations of motion are highly chaotic and very sensitive to any errors that we introduce. And when we use a numerical integrator, we're going to introduce lots of errors. And so it would seem like a nearly hopeless enterprise to try to integrate these things numerically, except for the fact that we aren't asking for accuracy in the usual sense, but rather we're asking for accurate averages. And so for this weaker requirement, it seems to be the case that there are methods that do well. It seems to me rather remarkable that this is true, but the Verlet method, among others, and there aren't that many others, seems to be a reliable way of calculating accurate statistics for these chaotic Hamiltonian systems. Now, a property that seems to be useful for doing this is the property of being symplectic. And there is a test, an algebraic test, that you can perform to determine whether or not a method is symplectic. If you write the integrator in this form as a mapping from one point in phase space to another, what you do is you take this mapping of a vector to a vector and you form its Jacobian matrix and you determine whether or not this is identically satisfied. And if it is, then the method is symplectic. Oh, I should mention that the problem, the analytical Hamiltonian system, has this property that the analytical propagator is symplectic. So this is simply a question of preserving a property of the original analytical problem. There's a weaker property than being symplectic called volume preserving. Volume preserving simply says the determinant of this matrix is 1, and there's even more compelling reason to believe that this is a property that we want our integrator to have. Let me now try to explain why being symplectic is a good property. As you've all observed, if we plot the energy as a function of time using a numerical integrator, it fluctuates. At least this is true for symplectic integrators such as the Verlet method. However, there is another Hamiltonian called the shadow Hamiltonian, such that this is exactly conserved by the numerical solution. The shadow Hamiltonian depends upon the integrator we're using. It depends upon the step size we're using. As the step size gets smaller, the shadow Hamiltonian gets closer to the original Hamiltonian. And it turns out that it is possible to construct very good approximations to the shadow Hamiltonian, as accurate as we'd like. And we can compute approximations to the shadow Hamiltonian and observe, well, whether it's conserved. This could help, for example, detect bugs in our program. It might also be useful to determine other deficiencies. So, for example, here is a plot for decalene simulation for 100 picoseconds. The green shows the energy, and you can see how much it fluctuates. And plotted are 4 approximations to the shadow Hamiltonian. This is second order accurate. This magenta is 4th order, dark blue is 6th order, and this straight red line is 8th order. So the shadow Hamiltonian, at least to this resolution, is exactly conserved by the simulation, showing that the implementation is correct. I'm going to show you another example that was recently computed. I'm going to digress slightly because these results excite me. I'm excited by numerical artifacts because that's my business. So this shows a simulation of flexible water. Flexible water is not commonly used by people doing biomolecular simulations, but we use it because it exaggerates numerical artifacts. And the simulation is for 30 picoseconds. And if you look at the energy, it fluctuates a lot. And people looking at that might think, well, this is random noise. But in fact, there's very little randomness in there. There is some randomness, but the randomness comes in a surprising way. This is related. You'll be doing an exercise this afternoon in which you'll be looking at a particular type of artifact that's visible in an energy time series, namely step-size resonance. So let's see what happens if we plot the shadow Hamiltonian for this. And this is an 18th order approximation to the shadow Hamiltonian. These are very cheap to compute, except for they require some memory. And what we observe is, to my eyes, very remarkable. It's pretty flat, but not quite. It has jumps. It looks piecewise constant almost. So what are these jumps telling us? Well, it could be a bug in the program, but more likely what I think is happening is it's showing us that the integrator has failed to resolve the dynamics at these points in time. Why? We don't know yet. Maybe there's a collision which just involves such high velocities that's not properly resolved. Maybe there's a transition in which would cause the Hessian to have a negative eigenvalue, and maybe that would cause problems. So that's 30 picoseconds. We could plot this for a nanosecond, and we get what looks like a piecewise constant function. And we get lots of events happening. Some of these events are rather dramatic. And so indeed, yes, it does seem that there is some randomness there. The randomness is probably in the jumps. And so over a long period of time, we are probably doing a random walk. And because it's entropically favorable for energy to increase, my guess is that even though this goes down in 1 nanosecond, that if you were to run this for 10 nanoseconds, it would probably go up. And one could probably from this even estimate how much the energy will drift over, 10 nanoseconds or a millisecond or whatever. So it does give us some kind of a handle on the accuracy of numerical integrators. Attempts have been made to find methods that are more efficient than the Verlet method, and these attempts have only been somewhat successful. One of the more successful ones is multiple time stepping based upon using impulses, popularly known as our reversible RESPA. This is a symplectic method. And this is an example of how it works. The idea, I think, can be described fairly simply. We take our potential energy function and we split it into a slow part and a fast part. The bonded interactions will all be fast. The non-bonded ones, well, these will have to be separately. Each of them will have to be individually split into a slow part and a short-range part. I indicated earlier how we might do a splitting of the 1 over r potential. And here's an example where, okay. Here is an example of where we have an outer time step, which is going to consist of 3 inner time steps. And each of these inner time steps can be viewed as a Verlet step of size 1/3 of the outer time step. And what we do is we do a Verlet integration and we change the value of the force. At integer values of our time, we use the entire slow part of the potential and 1/3 of the fast part of the potential in order to define our forces. At all other steps, 1/3, 2/3, 4/3, 5/3, we use 1/3 of the fast part. So in the long run, of course, we get the full force. So what is this doing for us? Well, this is saving us evaluations of the slow part of the force. It's only being done 1/3 as often as we would otherwise do it. And if most of the work is expended in evaluating the slow part of the force, then we have a great speed up, potentially 3 times. But in practice, this is not realized because in practice, we have fast methods for doing the slow part. So fast that the savings are not dramatic from doing this. Now, there was the hope that using multiple time stepping and using a step size for each interaction, which was adequate to resolve it accurately, that we could have great improvements in efficiency. However, this hope cannot be borne out because it seems like there's some intrinsic property of methods which are non-damping, that is, volume-preserving integrators, which says that the outer step size cannot exceed 1/3 of the period. There's no theorem, but there's fairly strong evidence that it would be hard to construct such a method. So there's some intrinsic limit on how long the largest step size can be if we want to use a volume-preserving integrator. And so in particular, if we use a charm force field and we don't have any constraints, that means that we can't exceed 3.3 femtoseconds. If we introduce constraints on the bond lengths for hydrogens, we can go to 4.6. Now, the Verlet method is even more restrictive. And in fact, it's even more restrictive than this because we want to make sure that we have enough accuracy, so we might just be using 1 femtosecond. So if we want to use NAMD, for example, we might choose a time step like this because it divides evenly into 25 and use a frequency of 3 for the ratio of the slow part to the short range part. Well, we might not be satisfied with this restriction. We might be willing to use a more speculative type of method for which we might expect less accuracy. We might be willing to use a non-symplectic integrator. Well, if we do that, that means that we are using a method that has damping. And to my mind, using a method that has damping is definitely the wrong thing to do unless we add a little bit of random noise. That is, if we're going to take out a little bit of kinetic energy, let's replace it, but perhaps with something random. So the next best thing to using a symplectic integrator, if we want to do kinetics, would be to add some weak Langevin coupling. And so we have worked on such a method in which we not only do Langevin coupling, but we do some averaging of the argument of the slow force. And others have pursued this. And using this idea of weak Langevin coupling, one can obtain an outer time step that is 16 femtoseconds and still get good accuracy, for example, computing a diffusion coefficient, which tests whether or not the temporal information is correct. A version of this is implemented in NAMD, in which it's possible to get an outer step size of 8 femtoseconds by turning all of these parameters on. And by choosing a damping which is 1/5 of a reciprocal picosecond, it appears that you do not affect, for example, the value of the diffusion coefficient. But it will have some effect on your long time accuracy. So having said that, I'll turn to constrained dynamics, say a few words about that. So with constrained dynamics, we have this additional term, the constraint forces. We have these additional equations to solve. And a very good method, a very popular method is shake. And in shake, the idea is that we determine these unknown Lagrange multipliers by asking that the new positions exactly satisfy the constraints. So this is a good method. It is symplectic. It is time reversible, even though it doesn't look like it's time reversible. There's a variant rattle which defines better velocities, but that's mostly cosmetic. We have these equations to solve. They're quadratic equations, but in many variables, you need an iteration to solve those equations. And you also have to solve them accurately, otherwise you get energy drift. So NAMD implements some constrained bond lengths. For waters, it uses an algorithm which I believe is analytical called settle, because waters are rather special and unique. And for other covalent bonds to hydrogens, it uses shake. And then there's the question of doing stochastic dynamics. One of the things you might have noticed about the shake method is that it is an extension of Verlet. And so for stochastic dynamics, we can also extend the basic Verlet method by differencing the first derivative here using a center difference. And so this is the BBK method. And it requires the generation of random Gaussians, which appear here. And in this equation, though, is this tensor. This is 3n by 3n. Inverting it could be very expensive. For some purposes, it's adequate to use a diagonal diffusion tensor, in which case inverting it would be trivial. In that case, there are better methods than the BBK method. The most efficient method is the method LN. Well, I should say there are notes that accompany this talk, and these notes have all the references, well, many of the references that you can refer to. If we just wanted a simple method, then the 1982 scheme of Van Gunster and Berensson is a better method than this, because in the case of strong friction, it still gives you an accurate solution. But this one, in the case of strong friction, becomes unstable. So the last topic is that of propagators. I discussed the kinetics question first because very often methods that are used to do kinetics can be used as propagators for thermodynamics. Now, Markov chain Monte Carlo methods is a topic that Professor Schlick will cover in her first lecture this morning. So let me just comment that there are some Monte Carlo methods that make use of molecular dynamics integrators called hybrid Monte Carlo methods. And these allow us to rigorously sample configuration space if the integrator has these properties of being reversible and volume preserving. Unfortunately, hybrid Monte Carlo methods, because of discretization errors, because of fluctuations in the energy, they have a high rejection rate, and this rejection rate goes up as the system size increases. And so this is one case where one might actually ask for more accurate integrators than would otherwise be justified. Another way to sample phase space is to use extended Hamiltonian methods. An example of this is Nose dynamics. In an extended Hamiltonian method, we not only have the usual variables of position and momenta, these are actually scaled momenta, but we introduce a couple of others. In this case, S is a scaling factor for time, and P sub S is the conjugate momenta associated with the time scaling factor S. And so we can write down a Hamiltonian like this. It's a function of many variables, and then just by taking partial derivatives, we can write down a Hamiltonian system. We can solve this numerically, and then we can use these values to calculate average values of observables. The Nose dynamics is not very popular, it seems. It seems that most people who do this sort of thing use Nose Hoover. However, this is not Hamiltonian, and so you don't have, and you can't use, it doesn't make sense to use a symplectic integrator. And it's been observed, in fact, that this does give some drift that would otherwise be unnecessary. I don't see any reason not to use Nose dynamics, even if it's just slightly less convenient. One of the advantages of using extended Hamiltonian methods is that you have this quantity here which should be conserved, and it can be monitored as an indication of whether or not you have a good simulation. This is not true if you use Langevin dynamics, which is another way of sampling from an NVT ensemble. If you use NAMBI, then Langevin dynamics with a diagonal tensor is the way to go. Let's see, NPT dynamics. This is the method implemented in NAMBI. Actually, it's more complicated than this. This is the special case where we don't have long-range forces and where we have a rectangular box and where we have just a pressure instead of a pressure tensor. But even then, it looks a little more complicated. These are the equations of motion that have to be integrated. This is the instantaneous pressure down here. That includes the variable. So this is the Langevin piston method.
Well, can we have 5 minutes for discussions at the end?
Oh, yes. In fact, the next lecturer said that I can go overtime if I want to, but she says she won't be here until 10. Yes, there will be time, because there's only one more slide. Okay, so this is the question. Well, another thing people like to compute are time correlation functions. And ideally, this is how you would do it. You would generate initial conditions from some ensemble using one of the propagators that I just discussed. And then using each of these initial conditions, you would do an accurate Newtonian dynamics simulation. And then you would take averages. And this is stated in the book of Ellen. Well, more often than not, this is not done. In fact, if you read the paper about the Langevin piston method, it seems like the authors of this paper are going to great lengths to remove artifacts that would be apparent artifacts in the temporal integration of the system. Now, I wouldn't be judgmental about what algorithms people use. However, what I do think is important is that when we make approximations, we should be open about the approximations we make and honest about the implications of those. The last part of my lecture concerns the question of how to use mathematical notebooks. Okay, we will not be using Mathematica per se for the numerical lab, but we will be using the notebooks because that's a very convenient way to do calculations. And so what I will do is by double-clicking on the notebook, start up Mathematica. You'll be given instructions on how to do this at the engineering workstation labs. It's slightly different there, probably. And so this is a notebook. I've actually increased the font size from what it normally is. And what you noticed is we have all this code here. And there's a bracket to the right there. You see this blue bracket here. And no, that's fine. And so there's a lot of code there. What this does is it defines two functions called f5 calculate and f5 plot. You don't need to understand any of this, although it's not so mysterious. And so to execute this, that is to have the definitions made, what you do is you just click on it and do shift return. Okay, you have to remember to do the shift with the return. Shift return. And that bracket is turned yellow momentarily. I don't know if you saw it. And now this has been executed. And you know it's been executed because over here, the word in has appeared with a 1. So that's the first expression which has been evaluated, or the first input cell. And now we have another input cell, and there's the bracket right here. We can execute this by putting the cursor there and then doing shift return. It doesn't matter where it is as long as it's in that input cell. And what this will do is it'll do molecular dynamics simulation using NAMD. We're just using Mathematica mostly as a front end. Behind this front end is some Perl script, and behind the Perl script are some executables. And you notice this is still running. It says running on top. It will take about 20 seconds. By the way, if you're tired of waiting for something to run, you go up to the kernel menu here. You come down here where it says abort evaluation is not highlighted because the evaluation is done. And you choose abort evaluation if you want to interrupt something. I mean, if you want to kill something. Okay, so that's done the calculation. Now we're going to view it. We're going to plot it. Whoops. And see, what you have here is an energy plot. But there's some numerical artifacts in it, and we're going to study those in this particular exercise. You notice this parameter 0? This parameter 0 is what you get if you don't join them with lines. But if I were to change the 0 to, I think 1 will work. We'll see. Well, I better not try. I never tried that before. We'll try 2. What this does is it joins every second dot. It'll do this for all the dots, and it uses 2 different colors. And this is what you'll get. So we have the same plot, but we've joined every second one. And now I'll change that to a 3. Oh, yes. We can make changes to the notebook by just putting the cursor there and just using the usual techniques. And execute. Okay, so 3 is dramatically different from 2, and we can go on and try 4. And I would say that's even better. Essentially, what we have here is step-size resonance. Essentially, what's happening is that the energy is cycling through 4 different values. And by plotting every 4th value, we can see that from the plot. And this is related to the highest frequency that's present in the system. So that's something that's actually to be expected from an integrator. What else can I say about the Mathematica? So not only can you edit the input cells, you can re-execute them by just clicking and then doing that. You can also do cut and paste. Suppose I want to have two different figures on at the same time so I can compare them. So I can just copy that, and then down here I can paste it. And then I can maybe change this to a 5, see what we get. We have a 5 there. And execute that. And now we have two different curves which we can compare. Okay, so that concludes my lecture. Are there any questions about this or what I talked about earlier?
Okay. So are there any questions? Okay, as usual, please speak loud and address the question to your colleagues as well as to the speaker. So in the yellow shirt.
I have one question about cell and grid matches.
Mm-hmm.
I try to understand you, and I think that those methods are based on Cartesian space. We are looking at everything, at solid and protein as something in space, instead of looking at something as a set of particles somewhere. So, do you know some other methods, and are those methods used because you are using parallel computing? Do you know some other methods maybe more efficient and maybe methods who are not using that cells or grids?
Okay. I know of no other fast methods, but I think you might be concerned about the fact that we are filling volumes with approximations, whereas in some applications, like electron engineering, this might not be the case where we have a volume full of charges. The charges might be on a plane, so we might use different techniques there. But in molecular dynamics, our charges fill volumes, and so these methods are very appropriate.
I know that, but why don't you think about, I don't know, the position of charges, but their distances and their relations. So instead of thinking about cells in space, you may think about set of particles. For example, you have 10,000 particles. You can divide that in 100 sets and try to do something like that.
Okay. Well, I just would say that.
Just one
Yeah.
set, which would be
Yes. Well, this is a pretty active, or has been a pretty active industry, generating fast in-body solvers. And I think that people have thought about the various possibilities. And I think the multi-level methods that I sketched out here for this application would be very difficult to beat.
Okay, there was another one. Really question.
When you plot this graph for energy fluctuations,
Louder.
yeah, these energy fluctuations
Mhm.
just for 200 time steps, the fluctuation seems to get smaller and smaller.
In this particular case, yes, they did.
So is it linked to some relaxation process, and will they eventually get really small, or these four energy curves will they get really close together?
I don't think so, but that's an experiment we haven't done. If there's an imbalance between kinetic and potential energy, that might affect the fluctuations.
Could you please elaborate on why a symplectic method is
Okay. An integrator is symplectic if and only if the numerical solution is the solution for shadow Hamiltonian system. So we end up exactly solving a system which has the same nature as the original one. Hamiltonian systems have this property, I guess, of what's the word? This when you do a long simulation, it spends an equal amount of time everywhere in phase space. And so you get the correct, if you do a long time simulation, you get the correct probability density of being anywhere in phase space. And also you can interpret what you've done relative to the errors in the force field, for example. Because you've made errors in the force field, you are working with a different Hamiltonian anyway, and so it's possible to make this kind of comparison.
When you were talking about the shadow Hamiltonian, you mentioned Hamiltonian fluctuation. I wonder what is the source of Hamiltonian fluctuation? It's some kind of thing related with the energy fluctuation or something else.
Okay. When we are following the numerical trajectory, what we are doing is we are moving on a surface of constant shadow energy. And there's another surface of constant energy, but it's different from the surface that we're moving on. And so if we observe the surface of energy from being on the surface of shadow energy, we observe the surface of energy going up and down. So that's part of it. The other part of it is that the shadow energy has a different weighting of kinetic and potential energy. And so as we have an exchange of energy between kinetic and potential, we observe these fairly high frequency fluctuations. At the far back?
Why are the Mosaic Hamiltonian?
It's due to the choice of variables. You can't, if you were to try to write down the differential equations based upon taking partial derivatives of that conserved quantity, you don't get, well, you can't get the system of equations by taking partial derivatives of the Hamiltonian, of the extended energy. Yes?
Do some of the references for your talk include how to evaluate or approximate the shadow Hamiltonian for
I think there's probably a reference in there to a paper that does. It's cheap, but a little complicated. In fact, to get the 18th order shadow Hamiltonian, we use Mathematica to generate the coefficients.
There was a question that was answered already. Okay, then you.
Could you elaborate on what NAMD does with the error for PME? When you select the tolerance, is it automatically selecting an equal parameter for the real space?
No, I think it's selecting a cutoff for the short-range force. It goes down exponentially fast, but it doesn't ever goes to zero. And so at some point you have to cut it off. The direct part of the calculation.
And the Fourier vectors can be chosen arbitrarily?
Okay. And the other parameters are the grid size.
Right.
And so there's some interpolation error in the sines and cosines, but I don't think that's quantified in NAMD at all.
Is there some way that you would recommend in assessing your thermodynamic propagators of, I guess, of quantifying how much of phase space you search?
Can you repeat the question?
Oh, yes. So the question is there some way of quantifying how much of phase space that you searched, or another way of asking that, is there any way of quantifying how fast you're doing the sampling? And so I don't know the answer to that question. There are papers that discuss this, and I think I would be able to find these papers. Although one way of thinking about it is, one way of sampling phase space is to do a dynamics simulation. And so this is a common way of doing it. So we can quantify how much sampling we've done by how much dynamics we've done. But that doesn't answer your question of how much of phase space we've searched, though. Mark? Yes?
Can you say a little bit more about polarizable force field? Imagine it.
Yeah, there's a paragraph about that in the notes. So I believe that they are implemented in Amber. I don't know how good the parameters are, though. Essentially, the problem that you're faced with polarizable force fields is you have to solve a dense system of linear equations. You of course do not do this directly. You do it iteratively. Or equivalently, you can set up some kind of extended dynamical system. It's extended dynamic, extended system, such that on the average, we get the solution of the system of linear equations.